Hi everybody, this is Dr. Niger with another Chem calculation screencast. This one's going to look at Dalton's law of partial pressures and mole fractions and the calculations that go along with those two topics. All right, Dalton's law of partial pressures deals with mixtures of gases. All right, to date, we've really been focused on a single gas within our sample, all right, but that's not really the case. I mean, most often we've got mixtures of gases. I mean, the air we breathe is a great example of that. All right. Gases, as one of their general properties, mix completely when given the opportunity and will fill their container completely as well. So what does that really mean? So if I have a container, and in this container I have a blue gas, which I'm going to call gas A, and then in addition, let's go red, I have a red gas, which I'm going to call gas B. There's not going to be any area of that container where it's all A, or an area of the container where it's all B. That gas, those particles A and B mix completely and fill the entire container. Now, while those gas particles are moving, they collide with each other and then they collide with the sides of the container. And when they collide with the sides of the container, we observe that as the pressure that that gas is exerting. All right. So for our previous examples, pressure was just the container, the interaction of the single gas with the container. Now what we have instead is a mixture. So we need to think about the total pressure within that container, and that's going to be equal to the pressure exerted by the particles of gas A plus the pressure exerted by the particles of gas B. Now, if I had a third gas in there, let's say gas C, then I would add that partial pressure in as well. All right, so on this side, we call these partial pressures, and we add them up to get the total pressure within that container. All right, so we can use this law, Dalton's law, to find the total, or if we know the total in one of the components, then we can figure out the partial pressure of one of the pieces within. All right, so if we think about the exertion of pressure, that pressure is coming because of the particles themselves. So when we talk about Dalton's law of partial pressures, we also could look at it from the vantage point of the mole, all right? And we do that by using something called the mole fraction. So I'm going to keep my container. We're going to think about it over here now, all right? And this funky X stands for mole fraction, and that's going to be equal to the moles of A divided by the total moles, except let's use our variable symbols instead. So moles of A divided by the total moles of gas within the container. And so that total moles is just like our total pressure. It's going to be equal to the moles of A plus the moles of B. All right, and that'll tell us the fraction of the gas particles within that container that are gas A. I could rewrite that for gas B. I would have the mole fraction of gas B equals moles of B over total moles. Depends on what you're looking for. All right. Now, hopefully, we appreciate that these particles of A are giving us the pressure of A. All right. So we can actually also think about this mole fraction, but think about it in terms of pressure. So it's going to be equal to the pressure that those particles exert divided by the total pressure within that container. All right. And again, that total pressure is equal to the sum of pressures of A and B. All right, so we really could think about mole fractions in two different ways. And this is nice because then it lets us set these two sides equal to each other, where the moles of A are equal to moles total and equal to the partial pressure of A over the total pressure. And that opens up some interesting calculations that we can do. All right, now, as always, watch your units. All right, the units must match for pressure. And N must be moles. All right, so make sure that you're watching out for those units when you work these problems. All right, so let's slide down to problem number 1. All right, we're going to try this one. This should be a simpler partial pressure problem. So we've got a mixture of CO2 and O2 with a total pressure of 1.75 atmospheres. If the pressure of CO2 is 785 millimeters of mercury, what is the partial pressure of oxygen? All right, so we've got a total pressure of 1.75 atmospheres, And we have a partial pressure of CO2 of 785 millimeters of mercury. And the problem's asking us for the partial pressure of the oxygen within that container. All right, so we've got a total pressure and then parts of that total. So this is a Dalton's law of partial pressure problem, where that total pressure is equal to the partial pressure of CO2 plus the partial pressure of O2. All right, now before I can work the problem and solve my unknown, I got to check my units. And if I look, I do have a unit problem. I've got atmospheres and millimeters of mercury, so I got to choose one way or the other. I think for this problem, I'll convert my millimeters of mercury to atmospheres. And I know that 1 atm is equal to 760 millimeters of mercury. Right, so if I do that conversion, I'm going to find that it's 1.03 atms. All right, so I go back over to my formula. The total pressure is 1.75. The partial pressure of CO2 is 1.03. And then the partial pressure of O2 is my unknown. So if I subtract 1.03 from both sides, I find that the partial pressure of oxygen within this sample is 0.72 atmospheres. All right, the problem doesn't specify what it should be in terms of units, so I'm just going to leave it in atmospheres. All right, so that's a pretty general Dalton's law problem. All right, let's slide down. Number 2 says a gaseous sample was collected near an active volcano and it contains water vapor, carbon dioxide, and sulfur dioxide. The total pressure of the sample is 1.25 atmospheres, and the partial pressures of water and sulfur dioxide are 0.75 atmospheres and 0.33 atmospheres, respectively. What is the mole fraction of CO2? All right, so let's see what we know. All right, so we have a total pressure of 1.25 atms. All right, we know that the partial pressure of water, in this case, is 0.75 atms. And we know that the partial pressure of sulfur dioxide is 0.33 atms. The problem wants to find the mole fraction of O2. Now, based on this problem, we don't know anything about moles. We haven't got mass, we don't have any moles. So when we talk about mole fraction of O2, we're going to need to come at it from the pressure side. So the mole fraction is going to be equal to the partial pressure of O2 divided by the total pressure. All right, now the total pressure I know it's right here, which means I got to be able to figure out the partial pressure of O2. And if I go back, I should be able to do that, right? Because I know 2 of the 3 partial pressures. So it should just be a matter of using Dalton's law. So the P total equals partial pressure of H2O plus the partial pressure of SO2 plus the partial pressure of, not O2, CO2. I kept doing that. CO2, CO2, CO2. All right, so I plug in my values. 1.25 atmospheres equals 0.75 atmospheres plus 0.33 atmospheres plus the partial pressure of CO2. All right, so if I add the partial pressures of water and sulfur dioxide and then subtract, I'm going to find that the partial pressure of CO2 is equal to 0.17 atmospheres. All right, so now that I know the partial pressure of CO2, I can come back to my formula for mole fraction. So 0.17 atmospheres divided by the total pressure, which is 1.25 atmospheres. Those units are going to cancel, and my mole fraction is 0.136. All right, now there's no unit here, which is reasonable because it's just a mole fraction. One thing to keep in mind, it's a fraction. A lot of people want to multiply that by 100 and make it a percentage, but it's not a mass percent or a mole percent. It's a mole fraction. So we just leave it as is. Okay?